In this paper, we propose face X-ray for more general face forgery detection. There are two major types of face forgery, face reenactment and face replacement. For face reenactment, it takes expression from source face. Other attributes like pose, background, identity are taken from target face, while for face replacement, only identity is from source face, and all other attributes comes from target face. The dataset we used is Face Francis++. It contains 1,000 real video and 4,000 fake video generated by 4 kinds of algorithms. Among those algorithms, face swap and deepfake are face replacement, while neural texture and face-to-face are face reenactment. Here are some examples from the dataset. As you can see, deepfake and face swap change the identity, while face-to-face only change expression. First, we compare human evaluation with the typical image classifier. As you can see, even a simple classifier like exception can achieve very satisfactory result. An average precision has to nearly 99% for all 3 kinds of face manipulation algorithms. But has this problem been solved? Our answer is no. Let's look at this table. If a classifier has a good result in one algorithm, it cannot generate to other algorithms. Like in the first row, if you train on deepfake, it gets a 99% result, but only get 50% on face swap, which is basically random guess. We should address that they are both face replacement algorithms. It's like even if you have a very good deepfake detector, one day somebody comes out deepfake plus, your detector will just fail totally. That's why we bring the face X-ray to solve this problem. Let's put away the number and talk about how to solve this problem. Our idea is looking for common defect. Most face manipulation methods was designed to process a small face area. Correspondingly, many deepfake detectors only focus on the artifact in that small area. But this is not the whole pipeline. You cannot just give users such a small region. In fact, for almost every algorithm, it will detect and align the face in the original image, and manipulate it, and finally blend it back to the original image. As most manipulation use this pipeline, we could detect those manipulations by simply detect the artifact introduced during the blending step. First, what is blending artifact? Every image has its own marks. It can come from hardware or software. If we merge 2 images, there is a strong possibility we can find those marks change across the boundary. As in this one, the middle column is noise level analysis, right column is error level analysis. The real face and blended face shows a very different pattern. A typical blending step is like a foreground face multiplied blending mask and a background face multiplied 1 minus blending mask. So we define face X-ray as blending mask multiply 1 minus blending mask and multiply it by 4 to make it ranging from 0 to 1. One major contribution of this paper is how to generate training data. Here, we propose a training data generation pipeline which only utilizes real face. We first detect the landmark of a background face and use it to search a foreground face which have most similar pose and expression. We then get an initial mask from landmarks and by conduct deformation and blur to get final mask. After that, we follow the equation in previous page to get our training data. Here, we simply use an FCN to predict the face X-ray and sum it together to get the final classification score. As in this table, row 1 and row 2 show that changeback boom won't solve generalization problem, and in row 3, train on face X-ray of the fake image can already improve generalization ability. And with the aid of the generated data, which is called BI in this table, we can further reduce generalization gap. Finally, the conclusion stays the same for all kinds of manipulation, and as it showed in the last row, we surprisingly found that our mask can achieve a pretty good result without any fake data. We have also compared face X-ray with some related work. As showed in the table, our masks have largely exceeded all previous state-of-the-art. Here is some example of our prediction. As you can see, our masks generalize very well between different blending shapes. Finally, we can come to the following 3 conclusions. Make sure to check our paper for more detail. Thanks for watching.